modular system containing 5 different modules for memory verification and effective context control in large language models. And my name is Andreas Ottem, and I'm 20 years old, and I'm also an independent researcher from Alta, Norway. Let's see. The first thing we're going to talk about is the challenge in RAG systems and LLMs. LLMs need good quality context. So if you write good prompts to it, it gives better answers. But if you introduce big clunky text and noise, it gives worse outputs. And then the problem in standard RAG is they often use simple method to find information, picking the most similar documents. And this likely includes information that isn't relevant, can be repetitive and contradictory, and it can be less accurate. And this could also slow down the process and increase the chances of hallucinations. And this is because in most RAG systems, they use a single step design, which is they find the most relevant information and they put it right into the prompt. And then RAG also struggles with growing amounts of information. So if the RAG system finds a lot of relevant information, it takes everything and puts it right into the prompt, which makes the LLM actually have to filter out the relevant information instead, which makes it then harder. Which makes it harder for the LLM to give a proper answer. And then another big problem we're going to tackle is distractor documents. These documents are information that sounds similar, but isn't actually useful for the answering. So if you were to talk about carrots with the LLM, it's going to take everything about carrots that's necessary, or everything that's appropriate to the carrots, but not everything that's appropriate to the question asked. So you're going to have a lot of information that's not relevant to what you're actually asking. And then we're introducing MeVe. And the benefits of this modular design is the transparency. You understand exactly why certain information was chosen, because you can go step by step between the 5 modules and see which modules actually did what. And then control. You can fine-tune each step towards your application for the best performance available, and this is almost necessary based on our testing, but you could make it more robust and need less refinement as well. It's based on how you implement it yourself. And efficiency, it makes it much easier for the LLM because it only gives the most valuable information to the LLM. It doesn't give all the unnecessary bloat, which is irrelevant. And this also helps it avoid common problems like confusing the large language model or giving it the same information twice or giving it contradictory information. And this is the MeVe architecture framework. I'm going to go step by step through the phases. You can follow me by using the picture provided on screen. And phase number 1, which is the initial retrieval. We've used the k-nearest neighbor search for this. And the purpose is to cast a wide net and find all the potential useful pieces of information. So this step is designed to take everything that is relevant and maybe not so relevant, but make sure we don't skip anything relevant at least. So this is just to make sure we get all the information we need to filter out from. And then the goal is to ensure that we don't miss out on anything. And then this goes to phase 2, which is the relevance verification. Also specifically a cross-encoder. And this is the filtering step. The purpose is to eliminate information that isn't truly relevant from the initial set found in phase 1. And this uses a specialized AI model called a cross-encoder and examines each potential document alongside the original question. And then it gives a score indicating how relevant that document is to the question. So documents with a relevance score below a certain cutoff, which we chose to be 0.5, are discarded. As you can see, after the phase 2, it goes into the triangle path here. And then if it's over 0.5, it gets approved. And if it is under 0.5, it gets discarded. And you can think of it like a bouncer to a club. Phase 1, which is the initial retrieval, is a friendly guy thinking highly of people and letting almost everyone in. While phase 2 is a secondary bouncer, which is more critical and separates the ordinary people from the VIP people and sends them to their VIP lounge. And onto phase 3, which is activated only if the cutoff is under 0.5. So if phase 2 is too critical and filters out all of the relevant information, we have a fallback retrieval mechanism to make sure the LLM actually has information. So if we strip all the information away, it's not going to have anything to actually answer with. So the fallback retrieval, which is BM25 OCopy, as we chose here, but this can be changed into other methods, is just to ensure that the LLM actually has something to go and use in for the answering. And then the text is combined. It isn't combined by any means or by any real reasoning behind them. It's just placed in the same document for phase 4 to actually do the real processing. And then phase 4, this takes all the verified documents from phase 2 and any documents found by the fallback mechanism from phase 3 and combines them into a single pool, which is sorted from most relevant to least relevant based on their score. And then the system checks for repetitive information. If 2 documents are very similar, and you can choose whatever percentage you want, and we chose 85 in this example, the less important one is removed. And the results, this ensures the final set of information is as informative and diverse as possible without unnecessary repetition, and maximizing the value of the actual context given. And then we go on to phase 5, which is token budgeting, where we use the greedy packing algorithm. And the challenge, large language models have a strict limit on how much text they can process at once. So we have made sure we have a budgeting phase 2. So we don't give it too much information. And this also makes sure that you can set your own budget if based on the project you are using. So if you have a project that needs a lot of information and it needs to have very good accuracy on the information, you can fine-tune it to the perfect level so it doesn't hallucinate while still giving you the best answers possible with the most amount of information combined. And then in our case, we chose 512 tokens as the limit, and it uses a greedy packing algorithm which structures from the most critical and useful information and then continues based on priority until you hit the 512 limit. And then we did an empirical evaluation, and how we tested it was we used a small part of the English Wikipedia, which was the first 100 articles. We had some resource constraints, so 100 was the most we could do, but 100 is still a lot, and it showed significant difference. So even though it isn't the 100% accurate, it's extremely close to 100%. So you have to take it with a small grain of salt, but still, it shows the difference. And then we compared it 3 different setups, which was internal LLM knowledge, which had 0 context efficiency, since it had no knowledge to answer the questions. And then standard RAG, context efficiency is how much text was sent to the LLM. And standard RAG was on 188.8, while MeVe was on 79.8. And then you can see here that it used on average 100 less tokens, or more than 100 on MeVe. And retrieval time, you can see the internal LLM, which is the baseline. It used no retrieval time since it has nothing additional. And then standard RAG used 1.12 seconds on average, and MeVe used 1.22 on average, which you can see is extremely close to each other. So it didn't actually give that much overhead on the retrieval time, even though it gave 57.7% less text than the initial standard RAG. And then to generalize this information, we did another dataset, which was HotpotQA. And HotpotQA is a multi-hop questions dataset, which is which is questions you need to combine information from several different documents into one to answer the question. And this is much more complicated than just a RAG system finding most relevant information and answering. It needs to collect from different places and then find the most relevant from more than one place. And the key findings we got here was it reduced the average text sent to the LLM by about 75%, which is even more. So it went from 308.6 to 78.5 tokens, which is essentially more than a third of the tokens on average. And retrieval time, even though it had this drastic of a reduce in tokens, it had a speed of 1.98 seconds versus the standard RAG that was 180. So it didn't introduce that much retrieval time, even though this is an extremely hard data set to use it on. So that's a positive. And then we did an ablation study to check which phase is needed to show that everything actually is needed. And then we started with a no verification, and then we skipped phase 2, which was the relevance verification step, and that was by treating all the found documents as verified. And here you can see on the graph on the right that it had almost as many tokens as the standard RAG. And this seems to have introduced the noise back into the system. So this leads right to the no fallback, which is the fallback retrieval, which is the information it gave if the phase 2 was too critical. And this shows that either it had no information or it had little information. So it shows that the phase 2 was too critical on its own. But if we combine both for the full MeVe, you can see that the average context tokens are much lower while still not going towards 0. It's not around the bottom, like the no fallback. And this shows that everything seems to be needed here. And onto the discussion. What are the challenges and future directions for this? Since this was just an experiment, it isn't explored fully. And some key insights we got from this was our context grounding proxy often indicated that the LLM was still generating answers based on the context that wasn't truly relevant. So it still introduced noise, even though we had all of these 5 steps. And this just shows that MeVe can't operate if it doesn't get good information, and standard RAG doesn't do that either. So we need some way to actually format the information to be perceived by the LLM on a proper way, instead of giving it a lot of text and hoping it gets it right. And then if we give it the most structure, it can do the best out of it. Another limitation, which is verification sensitivity. If it is too strict, it filters out useful information. And this could potentially lead to something that's more adaptable. Since in our example, we just used a very simple algorithm just to show that it's working. But if you made the strictness adaptable, so it understands when to be strict and when to not be strict, it could potentially make only the noise go away instead of actually removing anything useful. And this could be a useful approach in how to move forward, but this is not tested yet. And also combining the retrieved information can be noisy. So it's hard to know what information is or how the information should be structured to give to the AI. If the information is a little here and there, it can be hard for the LLM still. And this is something we still haven't addressed completely. And also the fallback limitations. If we use too simple of a fallback algorithm, like BM25 Okapi, it's one of the more simpler ones. And this, if we use a more sophisticated algorithm, it would probably take more time. But if the algorithm isn't too time expensive, it could be a good way to actually do this. Or maybe it could help the fallback algorithm not introduce noise again, since the fallback algorithm is just a in-case scenario. It isn't intended to be used too much, at least not optimally. And thank you. Are there any questions?